Mr. Theroux, in this video we're going to be introduced to something called the Poisson distribution in statistics. We're going to work through about 7 examples. You'll find timestamps to all of those examples in the description, so you can jump ahead to any one that you may want to look at. We're going to go from introducing the concept, talking about sort of the characteristics, how do you recognize that you're looking at a Poisson distribution as you're reading your word problems in statistics. Of course, introduce the variables and formulas, and then we're going to work through an example that kind of just gets you used to the use of the formulas in your calculator. A probability question that's also fairly straightforward for the Poisson distribution setting. And then example 3 is going to be involving some algebra involving the conditional probability work in there to kind of add some complexity. And then our last example is going to help you realize that through this type of variable in statistics, we're going to be, for a lot of questions, very reliant on our calculator. There's some commands that really speed up the process, but you really want to know those formulas, how they work, what the variables represent, so that when you get into some questions like near the end of our video, you'll be able to still answer those because you're not completely reliant onto the use of your calculator. Yes, did I say this? You'll also find a link where you can find all of my statistics lessons organized by topic and chapter, a nice organized list, not just a big long playlist with hundreds of videos. So here we go. Poisson distribution. If an event is randomly scattered in time or space, the discrete random variable x that models the number of its occurrences in a given interval follows a Poisson distribution with the parameter lambda. So we have x following a Poisson distribution, so that's a little piece above there, of lambda. And where, like say with the normal distribution, you have to define 2 variables, the mean and standard deviation. For the distribution of a Poisson, or with a Poisson distribution, you only have to define one variable, which is lambda. So what is lambda? Well, it's the rate parameter, and it is the expected number of events in an interval. And to calculate lambda, like you'll see as we get into some of the more sophisticated versions of our examples, it is going to, you might have to calculate and adjust some information given to you in the problem. It's the events per interval times the interval length. And that interval may be some type of interval of time or space. Okay, so you're reading the problem, you're trying to determine if it's a binomial setting where we have 2 outcomes, a set number of observations, independence, and a constant probability. Is it a geometric setting which is really closely related to a binomial setting, except you're going until you have your first success, so there's not a set number of observations? Or is it this Poisson distribution? Well, the occurrence of an event at a particular point in space or time is independent of what happens elsewhere. So you need that independence, like everything else basically in statistics. The probability of an event occurring within a fixed interval is constant. There is no chance that 2 events will occur at precisely the same moment in time or space. And in theory, this is how it kind of differs from a binomial setting, but is similar maybe to a geometric setting. In theory, the Poisson distribution has no upper value. Like in a binomial setting, the variable of x, the number of basically successes, over a set number of observations n will have an upper limit of n. So maybe that makes sense, maybe it doesn't. Let's add this in here. Some real life scenarios where you're reading the problem and you recognize that this is a Poisson distribution, unless it might be just blatantly stated that for you in the problem. But let's say the number of red lights run at a given intersection during a given period of time. So maybe we're not looking at maybe observing 100 cars passing through an intersection and counting the number of cars that run a red light. That might be something that is binomial. Not observing cars at an intersection until we find or observe our first car running a red light. It is the number of red lights run at a given intersection during a given period of time. The number of math errors on a randomly chosen page of a solutions manual. We all try to be, of course, exact with our mathematics. I try and make all my videos without errors, and yet, because I don't have my students kind of calling back and saying, hey, you just said something incorrectly, you know, I have to edit the video sometimes because there's an error. And it's really shocking how many times, especially when you get a new textbook, where you get those solutions and you're trying to teach out of the book for the first time and do those problems yourself. And even as a teacher, you start to doubt yourself because there's an error in the solutions manual, and it turns out, well, the error is in the solutions manual, not your own work. Anyway, the number of flaws in a given car's paint job. So these are all scenarios where you want to read that and recognize that it's not binomial, it's not geometric, it's a Poisson distribution. All right, let's get on to our first example coming up not quite right now. We got to get the formulas right and the variables defined and see those formulas that we're going to use as we go through the problems. No. So once we are told or we figure out that some variable x follows a Poisson distribution with a parameter lambda, the expected number of basically observations or events in the interval, just want to make sure I say it correctly, the probability that x is equal to a, I'm going to use a, lowercase a instead of lowercase x, because big X and little x, that's like notation my textbooks usually use, just gets a little bit confusing. So the probability that x is equal to some specific a is equal to e raised to negative lambda times lambda raised to the power of a over a factorial. And a is going to take on the values of values such as 0, 1, 2, and 3, and so on, remembering that in theory, the dot, dot, dot indicating that there is no, upper value, if you will, for a Poisson distribution. Now with a calculator, we're going to go to second distribution, or however the menus are set up in your calculator, and look for that Poisson PDF command. On a T84, it's second distribution. And the first number you're going to put in is that parameter, or lambda, and then the number of events you're looking to observe over a particular interval. Now, the probability that x is less than or equal to a, so a cumulative distribution function instead of a probability distribution function, is going to be equal to sigma, where t starts at 0 and goes up to an upper limit of a of e raised to the negative lambda times lambda to the t power over t factorial. Really, you can see these are the same expressions. It's just that you're going to repeat that process for the cumulative distribution function, where you're going from basically a down to 0 events in that interval. With your calculator, which is going to count down like it does probably with your model of calculator for your binomial CDF command, the probability that x is less than or equal to a is Poisson CDF, again putting in that parameter lambda and then the value of a. So what's this work going to look like? Let's just start working with the expressions and the formulas first before we build into more sophisticated problems. We are told that a variable y follows a Poisson distribution with a mean of 3. Find the probability of these particular events. Find the probability that you get y equals 4, that you observed 4 events over a given interval when it's expected that you will see 3, which is, by the way, going to have the highest probability of observance. So how do you calculate this? Well, looking at our formula here, thankfully with the air off for a few minutes, we have e raised to negative lambda, well in this case that's going to be 3, times, again, lambda, that's going to be that 3 again, raised to the a power, so 3 raised to the 4th power, over 4 factorial. Now that work is going to be nasty. This is an exact format. We're going to be using our calculator whether we work with the formula or the just simple calculator command. And ultimately we're going to get some kind of approximated decimal out of our calculator. So this is going to come out to be 0.168. But that is where the numbers are placed appropriately in our equation. Now with your calculator, how do you get that in there? You're going to do Poisson PDF, again entering the parameter first, 3, the number of specific events that you're looking to observe over an interval, which is 4, and that comes out to be, well, why am I pausing? It's the same thing. It's the 0.168. Now, just to add a little bit of extra difficulty here, we're going to look for the probability that y is less than 4 and just say, hey, be careful with the notation. This is y is less than 4, but you have a formula and a calculator command that gives the answer to the probability that x is less than or equal to a. So we have to convert this y is less than 4 into a less than or equal to situation. And so with this discrete random variable, what is equivalent to y is less than 4? Well, that means that the y value is going to be less than or equal to 3. So the number of events that we are going to observe over an interval can take on the values of 3, 2, 1, and 0. So this is equal to the probability that y is less than or equal to 3. And now that we have that written correctly, we can come over here and say, okay, go find that sigma notation with your 84. You're going to do something like go to the math menu, or alpha y equals, and then scroll over till you get, well, scroll over this way till you find that sigma notation. But we're going to be doing sigma, where t starts at 0 and goes up to, not 4, but an upper limit of 3. And what else does it say? We're going to be putting that into the expression e raised to negative lambda, or negative 3, times 3 raised to t, or, and you know, when you type this in your graphing calculator, you probably are not going to use the t, you just let it be x with the use of your calculator, but e to the negative 3 times 3 to the t power over t factorial. And if you get that entered correctly, that is going to give you 0.647. The calculator command, which I probably should have done that in blue here, since I put it in blue in the notes, is going to be, of course, CDF, put in the parameter, which we're told here is 3, put in the specific value of a that we're looking for. Well, that's going to be 3 as well. And of course, that's going to give you the same approximate decimal, 0.647. Okay, now we're going to have 2 more examples where we're just working with the formula and getting the phone. No, 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 no. No, 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 no. Now we're going to find the probability that y is greater than 4. Again, just pointing out that you need to be careful with your notation and how you read this, and just carefully convert it into a problem that uses the notation that we can easily or just simply work with. So we're going to find the probability within this Poisson distribution that y takes on the values which are greater than 4. Well, first of all, that's an inequality that's counting up, and your calculator is only going to be able to count cumulatively with those number of observed events within an interval counting down. So what is the opposite of observing more than 4, 5, or 6, or 7, or 8 events? Well, the complement, or the opposite of observing 5, 6, 7, 8, 9, so on and so on is what? 4, 3, 2, 1, and 0. So this is equivalent to, we're going to do 1 minus, because we're going to use notation which is the complement to this, which is 1 minus is the probability that y takes on, you know, that opposite of observing more than 4, which is observing 4 or less. And really, as long as you have these formulas memorized or at your disposal, that's pretty much the difficulty with this question. We're going to do 1 minus the sigma, where t starts at 0 and goes up to 4, of, as we see here one more time, e to negative lambda. So e to negative 3 times 3 raised to the t power over t factorial. And we're not going to put our calculator in a sort of like parametric mode to get a t to come out when we hit the variable button. We're just going to let, you know, as we type this into our t84s, this is probably just going to be with x and x factorial here in the denominator. But that's what it looks like in terms of formula work. We're probably going to be putting on our calculator 1 minus, not binomial, but Poisson, CDF, lambda first, specific a second. And when we do that, we are going to get the value of, making sure I wrote this correctly, approximately 0.1847. Okay, now I'm going to pause because I want to make sure that I wrote the right decimal in the previous example. Whew, okay, I did. So moving on to part D, we're going to find the probability that that y takes on the value of 5, given that y is greater than 4. So bringing in a recall of that probability rule that says the probability of A, given that B has occurred, is equal to the probability of A and B divided by the probability of B. Got to have to bring this back up in our memory bank, or maybe your teacher's allowing you to use a formula sheet, whenever we see that given that or that conditional probability notation in our question. Okay, so keeping that in mind, we're going to have to find the probability of y equaling 5 and y being greater than 4, and dividing that by the probability that y is greater than 4. Okay. Well, think about this. Y is the number of events observed in a particular interval, and if y is equal to 5, it is going to be automatically greater than 4. So I'm writing this out to kind of tie in with that probability formula that we were given and probably should know from previous sections, but really y can't be 5 without also being 4. So this is basically just the probability that y is equal to 5 divided by the probability that y is greater than 4. A lot of times, with questions, we'd have to do some kind of work here to find a value in the numerator, but if y is 5, it is by default going to be greater than 4. So really, this is an equivalent statement. Okay, well, that means that the algebra involved in finishing this problem up is going to be to figure out what is the probability that y is equal to 5. So again, it's going to be that e to the negative lambda, or negative 3, times 3 raised to the a power, so 5, over 5 factorial divided by, now in part C, we already found out what the probability of y being greater than 4 is. It was approximately 0.1847. So we already have some rounded off decimals in this problem. We're going to just go ahead and type this in the calculator by entering, in blue this time, Poisson PDF. Because we're not looking for an accumulation of events where we're going from 5 down to 0, but just specifically 5. Lambda A 5. That is going to give us approximately 0.1008, and then divided by the decimal that we already know, which is chalk down 0.1847, which gives our final answer is approximately equal to 0.5458. And if your teacher's happy with just a number answer, that's the answer. Or you may need to rephrase your question. The probability that we have y equal to 5, given that y is greater than 4, is equal to this number. I'm saying that, but now I'm just realizing there is no context to this problem. It's just the use of formulas. So there would be no reason to have to rewrite that in a context statement. All right. Really example 2, or if you're breaking down the parts of A, B, and C, example 5 coming up right now. So for example 2, the mean number of bacteria per milliliter of some liquid is 4.5. Just going to simplify and not worry about some kind of like units of measure here other than per milliliter. I'm sure there's more than actual 4.5 individual bacteria here, but let's just say that it is some unit of measure. Find the probability that in 2 milliliters of this liquid there will be fewer than 8 bacteria. So we don't have a set number of observations. We're maybe leading this into a binomial setting, but we do have a set value of space, 1 milliliter of some type of fluid. And we're just counting the bacteria in this set space. And we're going to find the probability that in 2 milliliters of this liquid, there will be fewer than 8. So this line right here, we're going to need to go back to that first set of notes where I said that you would have to calculate maybe possibly or adjust your lambda to meet a different size space or interval. And it's pretty simple. We're going to say here, recognize that we're in this Poisson distribution. We're going to let B be the number of bacteria in 2 milliliters of liquid, some liquid. And lambda, the lambda that coincides with my definition of B, is not going to be 4.5 because that was the expected number of bacteria in 1 milliliter of liquid. Well, we're just going to double that for the fact that we have twice as much liquid space. We're going to have 2 times 4.5, which of course we know is 9. So with our definition of B defined or given, and our lambda for the appropriate amount of liquid, we're going to find the probability that B is going to take on fewer than 8, which means that we'll need to recognize then that that is equivalent to the probability that B is fewer than 8 is less than or equal to 7. And now this actually now we have a word setting to kind of help you recognize that Poisson distribution setting, or Poisson setting, and now it's just going to like the previous questions that we did. So, and to calculate that, we're going to either be putting in where we have sigma, where t starts at 0 and goes up to that upper limit of 7 of e to the negative lambda, here for B is 9, times 9 raised to the t power over t factorial, or go ahead and recognize that we have that inequality symbol, of course. That's why I'm working with that sigma notation here. Or we got Poisson, CDF, cumulative distribution function, lambda first, and your specific A next, so 9 and 7. And that comes out to be, making sure I wrote this correctly, that'll come out to be approximately 0.3239. So, in this setting, in 2 milliliters of liquid, the probability that we will observe fewer than 8 bacteria is 32.39% if you are going to be needing to write an in-context statement. No. Example number 3. The word problems are getting longer. And here we're starting to move into the realm of you can't just be calculator dependent to answer some of these questions, and depending on the difficulty of the math class you're in. That may very well be the case, and probably so. Individuals arriving at a help desk are independent of each other throughout the morning. The number of individuals arriving per hour can be modeled by a Poisson distribution, I love saying that word, with a mean of lambda. The help desk is open for 4 hours. Now we know what basically our time interval is there. If exactly 5 people arrive for help over the 4 hours, find the probability that exactly 2 of them arrived during the first hour. And that is it. We are not given information in this problem to identify what lambda is. So how are we going to just simply rely on our calculator? We don't have enough numbers to plug into it. Okay, now let's see here. If exactly 5 people arrive over those 4 hours, that's a condition that has to be met to then even start considering the rest of this problem. So this is actually a conditional probability question. So we're finding that we're going to let x equal the number of people that arrived at the help desk, assuming to then number of people that got help. And what we're asked to find is the probability that that 2 of them arrive in the first hour, or 2 of them get help the first hour. This is kind of a small space, so I'm just going to say 2 in first hour. Given that you have 5 people getting help total. That's what we're being asked to find. Well, with that probability notation, right, the probability of A given B is the probability of A and B. So it's the probability of 2 in hour 1, or in the first hour, and 5 get help total, dividing by the probability of A and B divided by the probability of B, dividing by the probability that 5 get help. Okay, how are we going to work out this probability that 2 get help in the first hour and 5 get help throughout the entire 4 hours? Well, this notation is going to have to change, and we're also going to have to recall that probability rule, that the probability of A and B is equal to the probability of A times the probability of B. Well, this multiplication rule for the and here only is valid, only works if the events of A and B are independent. Well, the number of people that show up for help at any moment in time can, there had to be that independence, right, that we talked about in the first part of the question. So if we consider that 2 people showed up for help in the first hour, that should be independent to how many people show up each additional hour. So we can rewrite this top line as the probability that 2 get help in first hour, and multiply that by the probability of what? The number of people that got help in the remaining hours of 2, 3, and 4, the last 3 hours. Well, if we need to have a total of 5, if we need to have a total of 5 people getting help, and already 2 have gotten help that first hour, that means that 3 people, we have to have the probability of 3 people getting help in hours, 2, 3, and 4. So to find the probability that 2 arrived and got help within the first hour, given that 5 people got help in the total of all 4 hours, what we're going to be doing to solve this question is finding the probability of helping 2 people the first hour, and then multiplying that by the probability of helping 3 in hours 2, 3, and 4, and divide that by the probability that you help 5 people within those 4 hours. Okay. So, for this phrasing here, we're going to be writing out, remembering that the probability that x equals a is equal to e raised to negative lambda times lambda raised to the a power over a factorial. And we're talking about a 1 hour period, so our definition of lambda here, with a mean of lambda for that 1 hour period, arriving per hour, so that lambda is for the number of people that got help per hour, we're looking at e raised to negative lambda times lambda. The specific a that we're looking for is that 2 over 2 factorial. That is this right here. Now times that, we have to figure out how to write the expression, basically that the probability that 3 people get help in hours 2 through 4. Well, what is the expected number of people helped over basically a 3-hour period if the expected number of people getting helped in 1 hour is lambda? Well, just multiply it by 3. So we have e raised to the negative 3 lambda, and then we have here times lambda for the 3-hour period, or the mean for the 3-hour period of 3 lambda raised to the specific a. We need, if 2 people got help the first hour, we need 3 people getting helped in hours 2, 3, and 4. So a is basically 3 for this expression over 3 factorial. That is all over 5 people getting help in a 4-hour period. Again, the expected number of people getting helped is defined by lambda, and it's defined as a 1 hour period. So for a 4 hour period, our expected value, our lambda, is going to be 4 lambda. So in our denominator, we have e to the negative 4 lambda. I don't know why I use parentheses there, times 4 lambda raised to the 5th power. Because again, we're talking about 5 people getting helped within that 4 hour period over 5 factorial. Alrighty then. So really all we have to do is flip up that denominator and start cleaning things up. We have e to the negative lambda times lambda squared over 2 factorial, or just 2. 2 times 1 is 2, times e to the negative 3 lambda times 3 cubed is 3927 lambda cubed over 3 times 2 times 1 is 6. And then that is going to get multiplied. We're going to take this bottom fraction and flip it up and multiply by the reciprocal. So we have 5 factorial in the numerator, which of course is 5 times 4 times 3 times 2 times 1. We're going to do a little bit of reducing as we go along here, even though we're ultimately going to grab a calculator in the end. That's going to be that 5 factorial, flipping this up, changing the division to multiplication of a reciprocal, e to the negative 4 lambda times 4 to the 5th, not y, but lambda to the 5th. Okay, so when you multiply like bases, you add those exponents. So we have e to the negative lambda times e to the negative 3 lambda is in the numerator going to be e to the negative 4 lambda, but we have a e to the negative 4 lambda in the denominator down here. So it looked like really nasty here. We're starting to have a lot of stuff cancel out. We have lambda squared times lambda cubed. But then over here in this denominator, we have lambda to the 5th power. Well, lambda squared times lambda cubed is lambda to the 5th, divided by lambda to the 5th, and that's how we're able to solve this question, basically, and find the probability that was asked for in this question without actually knowing what lambda was. It turns out that it ends up just canceling out. We have 3 times 2, which is 6, so that's going to cancel out. And that's pretty much it. So we are looking at what? Well, we have 2, and this 4 is going to cancel out to be 2. So we've got 27 times 5 times 2 over 4 to the 5th, and that is going to come out to be, unless I have something copied wrong, we're going to check this here, approximately equal to 0.2637. Let's check that math. Okay, we got the right answer. I see why I was pausing a little bit. When I did this originally, I let the 4 and the 4 to the 5th in the denominator cancel out and make that 1 over 4 to the 4th. But we do have that same approximation. Last example coming up right now. It's the last example. Given that 3 times the probability that x is equal to 2 is equal to the probability that x equals 3, knowing that we're working with x, which follows a, forgot to write that, knowing that we have an x that follows a Poisson distribution with some kind of parameter lambda, show that lambda is equal to 9. Well, basically you're starting with probability notation here, and you don't have that lambda defined to just simply plug into your calculator. And with questions that say show that, they're not asking you to simply calculate this with the Poisson distribution with a 9 plugged in and multiply it by 3 and do it again with the probability that x is equal to 3. We're wanting you to see, or wanted to see from you, some basically like an algebraic proof, not just plugging in lambda equals 9 and saying, hey, we got the same answer for my calculator both times. That is not going to cut it. Okay, so we have 3 times the PDF command here, or sort of formula, if you will, the probability distribution function expression for the probability that x equals 2 is e raised to negative lambda times lambda raised to the a power over a factorial. we want to show that, or given the fact that this is equal to, again, we have a probability that x is equal to 3, so we're looking at e raised to that negative lambda times lambda raised to the power of a. So in this case, on the right-hand side, that's going to be a value of 3 over 3 factorial. Solve this. Well, okay, so we have 3 halves e to the negative lambda times lambda squared is equal to 3 factorial is 1/6 e to the negative lambda times lambda cubed. Well, e to the negative lambda on the left-hand side is some kind of unknown constant. We can divide, actually both sides, we can do this at the same time, divide both sides by e to the negative lambda by lambda squared. Those e to the negative lambdas are going to cancel out. When you divide like bases, of course, they cancel. So we have, and this is coming out over here, so we have 3 over 2 is equal to 1/6. This is one that's fallen away pretty easily. Lambda cubed divided by lambda squared. When you divide like bases, you subtract the exponents. So we have lambda. We're just going to simply multiply both sides by 6. And we have 18 divided by 2 is equal to lambda. So therefore, lambda is equal to 9, which is what we were asked to show. This is my last example. I'm Mr. True. Go do your homework.